Assalamu alaikum everyone. This is lecture 6 on digital control system. We are covering chapter 2, the Z transform. The Z transform is a very useful method for analysis and design of a digital control system, where the system is partly discrete time and partly continuous time. Now we started the inverse Z transform in the last class. One of the last method that is left is basically inversion integral method. So to proceed with that inversion integral method, we better start deriving the theorem first, and after deriving it, then we can proceed with the application of that theorem. Okay, so let's start some of the basic of complex variable theorem. We have to review, and based on those theorem, we can actually find out the inversion integral method. So the method is inversion integral method. And in some book, it is also known as contour integral method. Okay, so let's review the theorem of your complex variable first, then we can go for the derivation. Okay, so suppose we have an isolated pole Z0. So let me draw the diagram first. So this is our complex plane. Okay, so sigma j omega. So arbitrarily we have a pole at any particular location, and we're calling that as a Z0. So if we have an isolated pole, and if you can have a circle drawn across around that one, keeping your Z0 as in the center, something like this, and a even bigger circle, so that you can form an annulus, keeping Z0 as a center for both of them. So we call this one as a say sigma as gamma 1. We call this one as a capital gamma 2. So this shape in between two circle. Okay. So maybe one is radius R1 and the other one is radius R2. So this shape is known as mathematically annulus. So say we have something like this, even though slightly deformed circle, but assume that those are two circles. The radius of the outer one, say R1, and the radius of the inner one, say R2, with origin is Z0. So from the complex variable theorem, we know that for this isolated pole of a function f0, so if you have a function, complex function fz, and if we can expand this one, okay, within this region, some of the technical term I am just omitting, but you can always include those where you can write that your R is basically within this zone Z minus Z0. Radius is this one, R1. Also, we can assume that for the inner circle, Z minus the radius of the inner cycle is also can be given by R2. Okay, and obviously we have assumed that R2 is inside the R1. So these are the technical terms. Now, if we expand this function fz, which is actually a function within this annulus, if we expand this one using the Lorentz series expansion, okay, of this particular function fz, which is within that annulus, okay, about all z0. So around z0, if we try to expand this one using the Lorentz series expansion, then we can write something like this: fz equal to summation of n equal to 0 to infinity an z minus z0 to the power n plus summation of n equal to 1 to infinity bn divided by, or 1 by, you can write it this way as well, z minus z0 series expansion if it is true within that annulus. So as a comparison with this one, with your Taylor series expansion, just a comparison if you want to know what is the difference between the Lorentz series and the Taylor series, then you can write something like this. Just for comparison, Taylor series around around 0. So if you expand it around x equal to b, then you will have something like this. Okay, so what is the difference? As you can see, in your Taylor series, only we have positive exponential, and your expansion is something like this: 1 plus x by 1 plus x squared by factorial 2. So all the positive power exponential of x will be coming. Okay, so this is one of the example of your expansion. But in the Lorentz series, the negative exponential is also allowed. So in the annulus, where your function fz is analytic everywhere in this annulus, in that particular case, we can actually expand our function around any particular pole or point with this Lorentz series. And the coefficients a and b can be written as an equal to 1 by twice pi j. So this is your outer circle, enclosed by outer circle, fz divided by z minus z0 n plus 1 dz, where you are actually starting from n equal to 0 to all positive values to n. And dn equal to 1 by twice pi j, anti-clockwise encirclement of the inner circle, fz z minus z0 to the power minus n plus 1, where n starts from 1 to 3 goes on. So basically, as you can see, the coefficients are starting for A is basically A0, A1, A2, and goes on. And for B, basically starting from B1, B2, B3 goes on. So that in both cases, we don't have zero coefficient. That is why deliberately, in one case, we started from 0. In other class, it is started from 1. Okay, so this is how we have. So basically, Taylor series expansion or this part of your Lorentz series are identical, same, and they are assumed from n equal to 0 and higher values. Okay, so the Lorentz series expansion includes the negative exponentials as well. Okay. So now we are interested about this coefficient b, and specifically the first value b1. Okay, where if you take your n equal to basically 1, then you are going to get for n equal to 1, you are going to get b1, and the b1 is basically 1 by twice pi j. Then you have the encirclement of inner circle with fz z. Okay, so as you can see, if n equal to 1, then it will be actually vanish. So what will be left is this parameter fz dz. Okay, so this is one of our finding. What is b1? Okay, b1 is also known as actually residue, but we'll define it later. Let's proceed with the formula. What it says, as you can see, this is actually referring to the inner circle. Okay, but we are actually interested about the outer circle because of the fact that that will give you the complete integral, complete closed circle integral. So somehow, if B is for inner circle, somehow can we link it in the outer circle or not? That is what we have to see. And that will be helped by the theorem that is known as Cauchy-Gauze theorem. Okay, so Cauchy-Gauze theorem will actually help us in this regard to take this encirclement to the outer circle. Okay, so and this theorem is also sometimes known as the principle of deformation of contour. Okay, so you can just review some online tutorial out there based on your principle of deformation of contour, or a consequence of your Cauchy-Gauze theorem. So what we can actually see that in the first figure, the circle, that outer circle that we have drawn, that can actually simply replaced by any closed contour. So this is your inner circle, Z, your gamma 2, and the outer circle, not necessarily a circle, any particular shape can be there. Okay, so any particular shape can be replaced by your outer circle, even it will give the same result. Okay, so this is all about your the principle of deformation of the contour. Okay. Then, if we apply the Cauchy-Gauze theorem to this newly drawn diagram, then what you can find is that Cauchy-Gauze theorem says, so inside this area, the shaded area, the integral value should be 0, because the function fz inside this shaded area, fz is analytical throughout this shaded area. Okay, so in that case, without even doing the integral, you can say that the integral over the outer contour, closed contour, gamma fz dz minus the inner integral should be equal okay, so basically the summation of the integral should be 0, so you can just say that the inner integral value is basically equal to your outer integral value. I don't forget to put this counterclockwise sign. If the sign is changed, then the polarity will also change. So now fz dz. So so in the B1, we actually have written the inner circle. Now we can actually take to the outer circle, and not necessarily outer circle. We can actually make it to any closed curve. So we can write B1 equal to 1 by twice pi j. The counterclockwise encirclement of gamma with Fz. So this is one of the useful findings that will be helpful in the derivation of the inverse integral. And this B1 is also called the residue of the residue of Fz at pole Z0. So now if you have any closed curve, closed contour, it has multiple poles, say Z1, Z2, and goes up to Zm number of multiple poles enclosed by a curve gamma. So in that case, how it should look like, say any particular closed curve, so not necessarily any of shape, so you can choose any shape, and inside those one you have poles. Says this is Z1, then you Z2, Z3, Z4 goes on to say Zm. Okay, so these are poles, basically the centers. Okay, so Z1, and then Z2, Z3, Z4, and goes to Zm. Okay, so basically in these circles, the function Fz is not analytic, but in the shaded zone here, so in between your outer enclosed curve, that is gamma, and this small gamma 1, this is small gamma 2, this is small gamma 3, small gamma 4, and this is your gamma m. So apart from those small circles, the shaded zone, everywhere else, your function is basically analytic in the shaded zone. So here Fz is analytic. Analytic is also differentiable for the analytic. So now if you apply the Cauchy-Gauze theorem in this zone, shaded zone, so the integral of Fz over the shaded zone is 0, because we know that if it is analytic and if we integrate, then the result will be 0 according to the Cauchy-Gauze theorem. And because of that, we can write that the outer integral of your obviously counterclockwise with gamma of your Fz dz should minus the other summation of the rest of them. It's gamma 1 Fz dz, then gamma 2 Fz dz goes on to minus your gamma m Fz dz should be equal to 0. Okay, so we can just write that your overall integral Fz dz should be equal to the summation of all those integrals. Okay, so this is one of the important property that we obtain from Cauchy-Gauze theorem. So is it now if we can apply your the formula that you derived with B1, as you can see that these are actually the integration over this side is already achieved in this equation, which is this one. Okay. And in the other side, what we have is, in the other side where we have is B1. And also for the smaller regions, you can also find out individual B1s. So for the smaller one, we can say B1 of 1. For the smaller region 2, you can say you can obtain the residue of B1 of 2. Similarly, for for gamma M, we can obtain B1, the residue for the pole M. So individual poles are possible. So basically, we can write this in this side that this is basically twice pi j based on the previous B1 formula, that this is B1 residue of the pole 1 plus residue of pole 2 plus goes on to residue of pole M. And to confuse B11, B12, B1M, you can also replace them by capital K1, capital K2, and goes on to capital Kn. So this is our encircled, counterclockwise encircled contour integral of Fz dz. Okay. So this particular equation is known as, residue theorem. Okay, so now finally, let us go to the inversion integral derivation now with this property of your residual theorem as well as the value of the residue. We can easily, with the help of the Cauchy-Gauze theorem, we can finally go to the derivation of our inversion integral formula. So inversion integral for Z transform. So according to the definition of the Z transform, what you know that Fz equal to in the series basically k equal to 0 to infinity x kt z to the power minus k. Basically x0 plus xt z to the power minus 1 plus x twice t z to the power minus 2 goes on to x kt z to the power minus k plus, so infinite series. Now, to take help of the residue theorem and the Cauchy-Gauze theorem and the value of the residue, now we can just multiply this equation on the both side by z to the power k minus 1. Why we actually choose this value of z to the power k minus 1? This is related to this one because we want to achieve this value, xkt. Okay, inverse Z transform. The value of inverse Z transform is basically xkt or xk. So we're just taking here the time series expansion, but it can also be your number series. So since we want to have this one, somehow this constant value here, which is the magnitude or the strength at particular instant of kt, we have to actually bring this parameter to be z to the power minus 1, so that we can say that xkt is the residue of these functions. So for that particular value, to make this one as z to the power minus 1, we are multiplying this particular parameter z minus k with zk plus 1. So kk will be cancelling, okay, minus 1 here. So eventually our coefficient here will be basically z to the power minus 1. So if you multiply, what we will get in the both side, xz z to the power k minus 1 equal to x0 z to the power k minus 1 z to the power k minus 1 plus xt z to the power k minus 2 plus x twice t z to the power k minus 3, and it goes up to xk t z to the power minus k and continues. So as you can see, these are the negative values of z to the power minus, and if you proceed further, next one, it will be z to the power 0, and then with some constant obviously, coefficient obviously, and next one will be coming with some values with z to the power 1, then some values with z to the power 2. So as you can see, we have a negative expansion of your z as well as with positive expansion of z. So this equation actually can be said that it is an expansion, Lorentz series expansion of this particular function. So we can call this one as a Lorentz series expansion of the function f x z z to the power k minus 1. So whatever previously we were talking about fz is now this value, this function. So fz for this particular case is actually xz z to the power k minus 1. Okay, so don't get confused. It's sometimes okay, so sometimes because of the pen that we have with a tab, it creates this kind of trouble. Okay, so now it is k minus 1. Okay, so this equation can be called Lorentz series expansion of the function xz z to the power k minus 1 around the pole. Pole here is z equal to 0. Okay, so if we say that, then we can say that this is actually the coefficient of z to the power, the coefficient of the z to the power minus 1, which can be called as a b1. Okay, so we can say that our xt or function xt or xkt is basically, so b1 is the residue equal to the coefficient here xkt. So you can also have your number sequence. In that case, you can say xk as well, same thing. So xkt equal to 1 by twice pi j counterclockwise integral of c with fz dz. Now what is c? So basically c, we are just assuming a circle with radius, the suitable radius that encloses all the poles of xz into z to the power k minus 1. So where c is a circle, but as we know that it doesn't has to be a circle. It can be any closed surface or closed contour. But for simplicity, we're just saying that c is a circle that encloses all the poles of function fz. In this case, it is xz z to the power k minus 1. Okay, so all the poles. So all the poles, what does it mean? Maybe z1, z2 goes up to z to the power n. So all the poles are actually enclosed. Then we can write b1 in this way, and that b1 is basically nothing but that particular value. Now, This is for one particular incident, but if you have multiple of them, as I said, z to the power 1, 2, 3, m up to goes in that way. So how can we write that equation? So the whole integral of throughout the goes contour C of that particular function fz, which is in this case xz, z to the power k minus 1 dz is the summation of all the smaller circle that we can have, C1 of the function z to the power k minus 1 k minus 1 dz plus the next circle C2 xz z to the power k minus 1 dz, and goes on to up to nth of them, Cm xz z to the power k minus 1 dz. So basically applying the Cauchy theorem. Okay, so now as you know that this actually represents the B1 values, B11, this is B12, and this is B1n. So basically, or in terms of K, they actually represent K1, K2, K3. Okay, so we can write just twice pi j, K1 plus K2 plus goes up to Kn. Okay, so in the other side, what we have is the closed integral of the whole function with respect to the whole space where it is analytical. Okay, so now we can write easily that, and this is, we already have shown, this is nothing but our xk or xkt. Obviously, then you have to put 1 by twice j. So we can write that xk or xkt equal to 1 by twice pi j. So if you put 1 by twice pi j here, so basically they get cancelled out. So xk or xkt is simply the summation of these residues that we calculated. Okay, so we can simply write in that way, xk or xkt inverse Z transform is I equal to 1 to m, the number of the poles. Then we have the residue of the function fz, in this case xz, z to the power k minus 1 at pole z equal to zi of your xz, z to the power k minus 1. Okay, so there may be simple pole, or there can be a multiplicity of pole locations. So basically this is for a simple pole, how to calculate for a simple pole at z equal to zi, how to calculate the k. K can be calculated similar to the way we calculate the partial fraction. Z tends to zi, then z minus zi multiplied with the whole function, that is z, z to the power k minus 1. Now, if you have multiple poles, so for a multiple pole at z equal to zj, we can calculate of we have also mention of order or multiplicity of q. So q number of poles at zj, then k can be calculated as 1 by q minus 1 factorial. Then you have to apply the limit of z tends to zj with the derivative of dq minus 1 dzq minus 1 with the whole function being multiplied with the multiplicity, that is z minus zj q into the whole function xz z to the power k minus 1. Okay, so this is if you have multiple poles of multiplicity q, then this is how you have to calculate the residue of it. So bottom line is xk inversion integral. What it says us is that xk or xkt is simply figuring out the residues of pole of function xz z to the power k minus 1. So if you can find out the residues and then you just make a summation of that, and that will give you at z equal to zi. So that will give you the inverse z transformation. I know the theory is a bit complicated, and derivation involves the basic understanding of the complex variable theorems, but eventually it is applying the theorem is relatively very simple. We can just use see one quick example that will make things a lot easier. Okay, so example 2.16. What it says that obtain xkt. So you have to find out xkt for the following so they may not say that find inverse Z transform. So they may say that find xkt, which is same as finding the inverse Z transform of the following xz using inversion integral method. Okay, so if it is explicitly mentioned, then there is no way you can use any other method. So in practical, nobody will tell you, but in exams or while you're learning, they may ask to solve you. So what is xz given? Xz is basically z1 minus e to the power minus 80 z minus 1 z minus e to the power minus 80. So we have to find out the inverse z transform of this particular case, basically xkt or xk, whatever it is. And actually we don't know yet whether the output will be a function of time or sequence. So anyone can happen. So we have to figure out that. So let's go for the solution. First thing is that we have to find out xz, because we have to apply on z to the power k minus 1. So whatever the xz is given, you just multiply that value with z to the power k minus 1. Eventually it will be z, 1 will be cancelling out, z k 1 minus e to the power minus 80 divided by z minus 1 z minus e to the power minus 80. Okay, so now once we have it, now we have to find out how many poles we have. So if you take k equal to 0, 1, 2, 3, whatever the value of the k, so pole is always remaining same. So the denominator is a pole, and the denominator, that means we have a simple pole at z equal to 1. This is one pole, and the other pole is we have at z equal to e to the power minus 80. So these are the two simple pole we have. So now the formula for the simple pole, so we can write that our z transformation xkt is simply k1 plus k2. Okay, so what is k1? K1 is the residue of the first pole, and k2 is the residue of the second pole, and in our case, both of them are simple poles, so we can find out that K1 is basically limit Z tends to 1, then whatever the total function that has to be multiplied with that particular pole. So Z minus 1 multiplied with Z to the power K 1 minus e to the power minus 80, then Z minus 1, Z to the power Z minus e to the power minus 80. So this one will cancel out, then set the value 1, so it will be also 1, so it can be canceling each other with a magnitude of 1. Okay, so K1 is 1. What is K2? So basically, K2 is limit Z tends to e to the power minus 80, Z minus e to the power minus 80, Z to the power K, 1 minus e to the power minus 80, Z minus 1, then you have Z minus e to the power minus 80. So this is being cancelled out. So if you put the values that equal to the power minus 80, you can see it's just in the reverse order than this one. Okay. And also you have to put this here z equal to kt. So what you can write here is e to the power minus a kt. Then you have 1 minus e to the minus 80, and in the denominator e to the minus 80 minus 1. So it can cancel with this one with a minus 1. So what we are going to get is minus e to the power minus a kt. So your xkt, now we know that it is a function of time because we have time here, is equal to k1 plus k2 equal to 1 minus e to the power minus a kt. Don't forget to mention k equal to ranging from 0, 1, 2 for every values of k, obviously. So this is your solution of your applying the method of inversion integral, so which is relatively simple compared to the theorem that we have seen. So we will try to see a few more example related to this one, as well as some exception. And also one more topic is left. So I don't want to prolong this one, and let's keep this lecture short and then go with the other lecture to complete the inversion integral formula examples, as well as finding the solution of the difference equation. Okay, so see you in the next class, inshallah. Assalamu alaikum.